Okay, so let me first introduce the speaker. Our speaker now is Jan Dymara. He is a professor at the University of Wrocław. His area of research is differential geometry, specifically geometry of buildings. He has a number of papers about cohomology of buildings and of Coxeter groups. One of his main achievements was proving Kazhdan property, that is property T for large class of groups acting on buildings. Property T is a very important notion in geometric theory of groups and also in Lie groups. I mean, a very important notion. You have probably, some of you probably have heard about it. And the next great achievement of Jan is introducing Hecke von Neumann algebras to study L2 cohomology of buildings. Jan is mostly loved by the students and as one of the best teachers at our institute, as I think you will see right now. Okay, Jan, please, the floor is yours.
Thank you for the introduction and thank you for the invitation to speak here. So just to get some credits out, what I will talk about is will eventually come to some work that some project that I'm involved in with Tadeusz Januszkiewicz and Linus Kramer. And it's some parts of my talk will also tell you about some earlier ideas of Nekovaj and Ganji, Kramer and Tent, and some classical, will be similar to some classical stuff from differential geometry, but I'll do it in a simplified context. So now, what kind of question would I like to consider today? I'd like to consider a question: how can bundles twist over space? So a bundle consists of fibers, and the fiber could be essentially anything. And then I'd like to put these fibers over some base space, some topological space. Over each point of the space, I'd like to see a fiber, and as you move in the space, the fibers should move along. And then when you come around a loop in your space, this fiber may come back to the original position in a twisted way or by identity. And that's a phenomenon that I'd like to describe and show some algebraic tools to deal with it. So on the slide, you can see two examples of bundles. On the left, there's a trivial bundle, a cylinder. It has, it consists of green intervals that are mapped by the vertical maps to points in the circle. So over each point of the circle, you have a green interval, and as you move around the circle, those intervals move, and every interval can be identified with a neighboring one. So you can imagine that they are all of length 1, and then there's a canonical identifications of intervals that are close, canonical isometric identification. On the right, the picture is locally the same. So what you see there is a Möbius band. It is also decomposed into green intervals. And there is a map from the Möbius band to a circle, which squeezes each green interval to a point. For example, you could imagine that the circle consists of midpoints of those green intervals. And then you can actually squeeze each green interval to its midpoint. And then the whole Möbius band is squeezed to a circle. So I've drawn the circle downstairs, but you can imagine the map as I've described. And then again, neighboring intervals that are close, may be identified in a canonical way. They are same length, so you just use isometric identification. And using this identification, you can pick your favorite point in some green interval and try to travel around this band. And in the picture on the right, if you make such travel around, you come back to the original green interval in a flipped way, right? You don't come back to the same point unless that was the midpoint. But typically you come to the opposite point in the interval, while on the left you come to the same point. So that's one way to see the difference between those two bundles. And as I say, I'd like to present you a more general framework for considering this kind of question and some algebraic tools. Now, the tools come from algebraic topology. So the first part of my talk will be based on showing you some basic factors of algebraic topology, basic ideas of how you can detect non-trivial topology in a space. It will not be very similar to general topology. We'd rather like to look at features that are unchanged under operations like squeezing or stretching the space. They will be changed if you cut your space or if you glue some parts of it together, but they are stable under various deformations, which in general topology are, well, change your space. In algebraic topology, they don't change the invariance. So let me start with an invariant called the fundamental group. And I consider some space X. Let me draw it. Okay, so that's X. It may have some holes in it. And I'd like to detect those holes. So I'd like to consider loops in this space. So let me draw a loop. A loop is a map from a circle, S1. And well, there are many loops. So loops are continuous maps, but I'd like them to be based. So in the circle, there's a distinguished point S0, and in the space, I'd like to have also a distinguished point X0. And I'd like only to consider maps that map S0 to X0. So loops will start at some fixed point, and then they may travel around the space, and eventually they should come back to that point. Okay, so these are loops, and a loop may go around a hole, and then in some sense it tells you that the hole is there, but there are many loops going around a given hole if the space is large. So we'd like to consider them up to homotopy. So homotopy is a, well, scientific way for deformation. So these loops, we'd like to deform these loops and consider loops that can be deformed one to another to be equivalent. And so let me be a bit more precise about this homotopy idea. Okay, so suppose I have some space Y. It could be a circle, like on the previous picture, or something else, some general space. And I consider I have two maps from this space to my X. So one of the maps is F0. Let me draw it here. There's some F0 going from the Y, which is the lower end of my product. So the space that I've drawn is the product Y cross 0, 1. And there's Y cross 0 as the bottom part of the cylinder and Y cross 1 as the upper part. And I have two maps. So one is F0, the other is F1. So they are originally just maps from Y to X, but I can put this Y as the bottom and the top part of the cylinder, and then ask whether this pair of maps extends to a continuous map on the whole cylinder. Okay, so that's a capital F, which is called the homotopy between these two maps. If it exists, then the maps are called homotopic. And the requirement is just that this capital F should be continuous and coincide with those two F0 and F1 on the ends of the cylinder. So you can think about this as of a deformation, say in the following way. You look at some cross section of the cylinder, some horizontal cross section, like y cross t, what happens at level t, and this will give you a map from y to a space x. And as t varies, these maps vary continuously and go from F0 to F1. So that's a deformation, and homotopy is a way to make precise the idea of deformation. So that's the equivalence relation that I'd like to consider in loops. I will consider loops equivalent if they are homotopic. Sorry. So the formal definition is that the fundamental group is just the set of homotopic classes of loops, and let me stress they're based. So each loop maps a fixed point in the circle to my favorite point on my space X. And then I use the word group because loops can be multiplied, or the homotopic classes may be multiplied. So let me try to illustrate that as well. Here's my space X. It has this base point X naught. And then I draw a circle in two colors. Okay, and I have two loops in my space. So one starts at X0 and comes back to itself. And the other also starts at X0 and goes back to there. Then I can compose these two loops in the following way. I define another loop, a map from the circle to my space X, so that it maps the upper semicircle, the red one, to the red loop. And then, okay, when you come to the point which is opposite to S naught, you are back at S naught, back at X naught in the space X. So then you can start going along the green loop. Okay, so the red part goes to the red part, the green part goes to the green part. And together it gives you, again, a loop in your space. So you should travel through each loop twice faster than originally, and then you can go through both of them while you travel around the circle. So that's a map which defines multiplication. Okay, and it's a fundamental exercise to check that it really is a group. So for example, if you try to check associativity, it does not work on the level of loops, but it does work on the level of homotopic classes. And similarly, if you try to find the inverse element, so the neutral element is the constant loop, the map that maps the whole circle to the point X0. And if you have a non-trivial loop and try to find the inverse, it will be the same loop but traveled in the opposite direction. If you compose those loops, then you get the loop that travels along the original loop and then goes backwards. So that's not a constant loop, but it is homotopic to the constant loop. So homotopy actually turns this multiplication to a group structure. Okay. So let me give you an example. The first example to compute is the circle itself. So let's say I have S1, and I also use loops that go from S1 to S1. You can use the same base points, and then there's a family, a very natural family of maps, which in complex coordinates can be described by the formula z goes to the nth power of z. So I'll call this phi n. And well, it just travels along the circle n times around. in the same direction. If n is positive, it travels anti-clockwise. If n is negative, it travels clockwise with a constant speed and it comes back. So that's a family of loops in the circle. And you can probably imagine that, in fact, any map from S1 to S1 is homotopic to exactly 1 phi n. So one way to visualize it, to try to convince oneself that this is so, would be to imagine that this red circle from which you define your map is made of a spring, of some elastic material. So, and then you perform a map. You map it to the blue circle just by stretching this spring and gluing it. So you imagine that, let's say, you place some electromagnets along this blue circle, and you can stretch a spring attached to the magnets, and then, or maybe go back with some part of the spring, go forward, and so on. You can sort of put it on the blue circle in the same way as your favorite map. And then you turn off the magnets, and the spring starts moving. Okay, it starts moving towards the position of constant tension, and it will move to one of the positions of the map phi n. Okay, it will eventually stabilize, and in the stable position, the tension will be constant. The tension constant means you get a map of constant speed, and that should be one of the phi n's. So that's not a mathematical proof, but it's a physical argument. There are mathematical proofs also, but they are a bit more involved. Okay, so in this way, we assigned a group to every topological space with a fixed base point. And another feature of this is that it's a functor. So whenever you have a map of topological spaces, a continuous map, this map induces a homomorphism of those groups. So let me try to draw this as well. Okay, have a circle. We have two spaces. There's X, there's Y. And you first have a loop near space X. Okay, let's say it's called gamma. And then there's a map from X to Y, which, let's say, is some map F. Then you can transform the loop via this F and get some loop in here, which is given just by composition. So that's how you transform loops in X into loops in Y. You just push them forward via this continuous map F. And it's, well, quite easy to convince oneself that if you deform gamma, F composed with gamma also gets deformed. You can just compose the deformation with your continuous map. So loops that are homotopic in X are mapped to homotopic loops in Y. And therefore, this map induces a map of fundamental groups. And then the law of composition going around one loop and then the other loop, it's also preserved by this procedure. So the map between fundamental groups is a group homomorphism. Okay, so in that way, I described you one of the basic functors of algebraic topology. It's a functor in the sense that it assigns a group to every topological space, and to every map of spaces, it assigns a group homomorphism, a homomorphism of the corresponding groups. And then a feature that I will use in a while, and I haven't written it, is that it respects compositions. If you compose two maps between three spaces, then there are corresponding three groups and group homomorphisms, and the homomorphism corresponding to composition is a composition of homomorphisms. It really is like translating the topological picture to the algebraic picture. Maps go to homomorphisms and compositions go to compositions.
There is some fixed point that every loop starts with this point?
Yeah, that's. I'm a bit sloppy about it, but yes, in fact, I should say that this works for pointed spaces. So on the topological side, I should have a space with some distinguished point, and my maps should map distinguished points to distinguished points.
Okay. Can we do it like that? That in this equivalence classes, we find some loop that goes through this point, and do it without fixing some point.
Get something different.
Maybe if there are two connected components, then we can have a loop in one and it never crosses.
Then you should treat them separately. So in each of them, you can distinguish a point in one of them, and then the fundamental group tells you something about that component only. You could use a point in the other component, then the fundamental group will tell you something about the other component. There's a more general notion of a groupoid, which serves well for the purpose of non-connected spaces, but typically it's enough to consider each component separately, and then what I'm telling you is quite good.
Okay, thanks.
Another question. So to finish talking about the fundamental group, I'd like to show some application. Why are those functors introduced and what they can give us? So they can translate some complicated topological question to an easy algebraic question. One of the easy examples is the Brover's fixed point theorem for a two-dimensional disk. So the theorem says that every continuous map from a two-dimensional disk to itself has a fixed point, has a point which is mapped to itself. And the proof is as follows. So first, you construct a certain auxiliary map. So if it was not so, then you could find a map from a disk to a disk without a fixed point. That would look, let's say, like this. Whenever you pick some x in your disk, and there's an f of x which is different. And then what you do is you draw an interval through those 2 points, starting at f of x, going through x, and you continue it until you hit the boundary of the disk. And the point where you hit the boundary is what I call g of x, and that defines you a map from a disk to its boundary. Notice that if you are on the boundary, your x prime, let's say, is a point on the boundary, then f of x prime is somewhere in the disk. You draw this interval, and the point where you hit the boundary is x prime. So x prime is the same as gx prime. So this map G maps the disk to its boundary, and points on the boundary are fixed. So let me summarize that by the following diagram. There's the boundary of the disk, which is S1. Maybe I'll write S1. Right? The circle, the boundary circle, can be included in the disk. So there's an inclusion map. And then we constructed this G, which maps the disk back to a circle, back to the boundary. And the composition of those two maps is identity. Okay? If you take a point on the boundary, treat it as a point in the disk, and map it through G, you come back to the same point. It doesn't move it. So there's a diagram of spaces and maps. There are, well, 3 spaces, 3 maps. They are continuous, and the composition of inclusion and G gives the identity. Now apply pi1 to this diagram. So compute the fundamental group of each of these spaces. So the fundamental group of S1 is Z, as I told you. The fundamental group of D2 is trivial, so that requires some easy argument, but a loop in a disk can be deformed to the constant loop, just along straight intervals. And then the fundamental group of the circle is again Z. And here you have a map corresponding to identity. So identity on the level of spaces induces identity on the level of fundamental groups. So if you had F, you would have G, and if you had G, you would have this diagram of maps in the middle, and from that you would get a diagram of groups and homomorphisms that you have on the right. So these are three homomorphisms. For the horizontal one from Z to the trivial group, the zero group, and then back from zero group to Z, and the composition of those should give you identity. So that's not possible. And therefore you get a contradiction here. And the contradiction tells you that every F should have a fixed point. Okay, so
maybe I have one remark, since this is quite striking that in fact we don't use any details of the construction of pi1, we just use the functoriality. So somehow this is a quite abstract argument. It also works for homology, yes, and
yeah.
Only the only two facts which we have to know is that for a circle this group is non-trivial, and for the disk is trivial.
Yeah, and then that it's a factor that really composition of maps corresponds to composition of homomorphisms. That's crucial in this argument. Okay. Okay, so that's all I want to tell you about the fundamental group. The next step is I'd like to talk about homology, because one of the features of this twisting phenomenon, this investigation of how fibers can twist over space, is that initially you think it is connected with the fundamental group, right? Those twists occur over some loops. You go around a loop and there's a twist of a fiber. But in fact, it turns out that in some sense, the twists can occur over high dimensional cycles, high dimensional pieces of your base. And to capture that, you need some high dimensional invariance. So you'd like to have some high dimensional cycles in your space, so detect some high dimensional loops. And the first obstacle is that you can imagine various shapes of those. You could have spherical cycles, or you could have toroidal cycles, or maybe genus 2 surface and so on. That's just two-dimensional things. And as the dimension goes higher, it's even harder to imagine with all the possible shapes. The idea is to, well, not specify shape a priori, so to build a theory which would incorporate all these shapes, but we don't use them in the construction. We just use simplices. And this space will be somewhat automatically built from simplices in your X that you'd like to consider. So what are simplices? Okay, I have some pictures. So these are certain spaces that, well, they occur in every dimension, and the lower dimensional ones are just point, interval, triangle, and tetrahedron. And then there are high dimensional counterparts of that. So an n-dimensional simplex can be defined as the convex hull of versors in Rn+1. In the n+1 dimensional space, you can take the versors and take the convex hull. So to see an interval or a triangle in that way, you can look at the pictures that are below them, and you can see that indeed these shapes appear in a high dimensional space in a more symmetric way. So a triangle is a bit, a triangle on a plane is not really symmetric with respect to coordinate axis, but if you put it in R3, you can restore the symmetry somehow. So it's convenient to define the high dimensional things in a symmetric way. And the convex hull definition gives you that. So you can do that in every dimension. And these are the building blocks. From this kind of blocks, you can build spaces, and that's already appeared in some talks here. You can use simplices to glue various topological spaces. Just take a bunch of simplices in every dimension and glue them along their faces. You can build various interesting spaces. But you can also use them as sources of maps to a space X, and those maps will try to build some cycles in the space. Right. So those maps are called singular simplices. So what's a singular simplex? It's a map from a simplex to a topological space, continuous map. So let's say I have some simplex. On the other side, I have my space X, maybe with some holes, and then I just take a continuous map. Right, so that's called the singular simplex in my space X. There are, of course, many such things, just as there were many loops in X, there are many simplices, singular simplices. And for those, I'd like to build cycles. So, okay. So the first step is, is to define the chain group, the n-chain group of X, or a group of n-dimensional chains. And that's a free abelian group whose base is the set of all singular simplices in X. So I consider all singular simplices in my space. And then I'd like to consider the free abelian group whose base is that set. So in more practical terms, I just take formal combinations, formal sums of those simplices with, say, integer coefficients. Finitely many simplices, each can be multiplied by an integer and form a formal sum like that. And those formal sums can be added. That gives me a huge abelian group. That's the chain group, singular chain group, SNX. And then I'd like to find some cycles in my space. So cycles will be some special chains, and to tell you which chains will be considered cycles, I need a boundary map. So for a singular simplex, I will define a boundary. And the boundary comes from restricting the singular simplex to its faces, to its codimension 1 faces. So on the picture, you can see a triangle, which is mapped to space X. It's a singular simplex of dimension 2. And then this triangle has 3 faces, 3 facets, 3 one-dimensional faces, 3 edges. And you can restrict the map sigma to each of the edges. And in that way, you get 3 one-dimensional singular simplices in X. To keep everything formally correct, you'd like these maps to be defined on the standard one-dimensional simplex, on the standard interval. So you have to compose this sigma with the map which identifies the standard interval with the edges of your triangle. So there are 3 edges, there are 3 maps called iota 1, iota 2, iota 0. And you compose sigma with those. In that way, you get 3 one-dimensional singular simplices. And the boundary of sigma is a combination of those. So you put some signs there, but let me not go into those signs. It's just that it's just a combination of those boundary restrictions of sigma. So this is another motivation for introducing this chain group, right? The boundary of a single simplex is a combination, is a sum of several lower dimensional simplices. It's not a single lower dimensional simplex, but a combination. So I need a place where these combinations live, and that's the n-1st chain group. The boundary of a simplex is naturally an element of the n-1st chain group. And then, well, we define the boundary of a simplex. Now we can extend that to homomorphism. So for any chain, you can define the boundary just by saying chain is a combination of singular simplices. You apply boundary to each of those simplices and adapt the results with the same coefficients that were in the original, present in the original sum. So that gives you a homomorphism from the nth chain group to the n-1st chain group. And this boundary is the operator that lets you define cycles. So a cycle will be a chain whose boundary is 0. And again, I have a picture which shows you a part of some cycle. So there are 2 red singular simplices of dimension 2, and they share an edge. There's this green edge, which is common to both of them. So if in some chain you see those 2 simplices, then when you compute the boundary, the green edge appears twice in the boundary of the simplex on the right and in the boundary of the simplex on the left. And if those simplices are well with correct signs, then these appearances of the green boundary will cancel. So if you calculate the boundary of the whole cycle, this green edge will appear twice with opposite signs, and that will cancel. So in that way, simplices can build up cycles. If you imagine that there are more and more red simplices around, and every edge is part of 2 triangles, then that will form a cycle. The boundary will be 0. An algebraic definition is just a cycle is a chain whose boundary is 0. All right. And then the next step, the next point is that cycles can detect holes. There's a question in the chat. Okay. The cycles cover the entire space. Well, yes, they do. And so you could do a trivial thing. There are simplices that map, say, the whole simplex to a point. Right? So if you want your cycle to go through a point, you can use a constant simplex. But that's not very interesting. But okay, you have all the possible singular simplices in your complex, all the possible maps from a simplex to a space. So these may go through any point you want, and therefore, as there are all of them, you can build cycles everywhere in the space. Okay, maybe let me mention that there are various cohomology theories, and for good spaces, they all give you the same results. And what I plan to concentrate today on, what I sort of assume implicitly, is that I deal with good spaces. So things like finite simplicial complexes, for example, would be pretty safe. And for those, all homology theories give you essentially the same. But if you go to some pathological spaces, like the Warsaw circle, things that you know from general topology, then there are differences, and there might be homology theories that are better equipped to deal with such spaces than what I'm showing. Okay, so please think today that spaces are nice. Okay. So coming back to the picture, one of the problems is that 2 cycles may detect the same hole. So in this example, you can see 2 cycles that go around some hole in my space. There's a blue hole in X, and the green cycle and the red cycles are going around it. So in a sense, they are detecting the same topological feature of my space. There are 2 different cycles. So in the fundamental group, if I was in the fundamental group, I would say these are homotopic. And so they give the same element of the fundamental group. So I'd like to say something similar now. And the thing that's usually said in this context is that, okay, there is the difference of these cycles is a boundary. So let me try to draw it. Okay. Draw a triangle like that here, and then another triangle here, another triangle there, and so on. In that way, even though the cycles are different, the difference is not topologically relevant, and you see that by seeing a two-dimensional chain whose boundary is the difference of these two cycles. So this two-dimensional chain will tell you that you can actually identify, you want to identify the green cycle with the red cycle. So cycles are called homologous or equivalent if their difference is the boundary of something. And the definition of the homology group is just that. You look at all cycles, they form a subgroup of the chain group. And inside this subgroup, you have a smaller subgroup of boundaries, and you divide cycles by boundaries. So this division tells you that if two cycles differ by a boundary, you will identify them, you will regard them as equivalent. They will be the same element of the homology group. More algebraically, those maps delta n, the boundary maps, well, they went between the chains group, and cycles are the kernel of delta n, images are the image, boundaries are the image of delta n plus 1. You just divide the kernel by the image. So that's the homology group. Okay. So what is a bit difficult when you look at these definitions is that there are loads of singular simplices. There are many, many ways to map a simplex to a space, and you can have no hope of, checking all of them and finding all cycles. And these groups are just unmanageable. The good news is that if your space is a simplicial complex, if it is built from simplices by gluing them along faces, then you can actually consider just the simplices for the complex, just the simplices that you glued together to calculate homology. You don't have to consider the weird maps. You just consider the maps that map simplex to the building blocks of your space, the blocks that you use. And there are, well, in a finite simplicial complex, there would be finitely many of them, and then you can do calculations. So, for example, sphere S2 is homeomorphic to the boundary of tetrahedron, boundary of the three-dimensional simplex. So there's this blue drawing, the boundary of a tetrahedron. It's a finite simplicial complex, so it's a triangulation of a sphere, an expression of a sphere as a finite simplicial complex. There are 4 vertices and 6 edges, 4 two-dimensional faces. So you can calculate those chain groups and maps and get an answer which will be the same as if you used all singular simplices in the sphere. So here, for example, the answers are as follows. The zeroth homology group is Z. So the chain group consists of combinations of the 4 vertices, but in fact, any 2 vertices are equivalent because a pair of vertices is joined by an edge, and the boundary of that edge is the difference, one endpoint minus the other endpoint. So using those differences, you can change a vertex into a different vertex, and therefore you can move all vertices to just one vertex, and the sum of coefficients is the only thing that's left. So this zeroth homology group is just the integers. And corresponds to the fact that the sphere is connected. So this Z is in the first power, and that power tells you that there's just one connected component. So for every connected space, H0 will be Z. H1 is trivial. So that's a bit maybe harder to see, but one-dimensional cycles can be decomposed into boundaries of triangles. One-dimensional cycles in this tetrahedron, these are just sums of edges. And the fact that it's a cycle and not just a general chain is that when you look at, say, edges meeting at a vertex, then the sum of coefficients should be 0. Right? The vertex should cancel when you calculate the boundary. And that just tells you that, okay, you can sort of make a partition of those coming edges into pairs corresponding to triangles and well, okay, maybe I shouldn't go into details, but all cycles can be constructed from boundaries of the 4 triangular faces. And then in dimension 2, you see the group Z, which comes from the 2-dimensional cycle. That's quite easy to see. To form a 2-dimensional cycle, you just have to take all the simplices. You take one triangle, it has an edge, so you need to take the neighboring triangle, and you just go around, take all the simplices, and that's essentially a unique cycle. So any other cycle is just a constant multiple of this one. So that gives you Z, as there are no 3-dimensional things, so there are no boundaries in dimension. And then high dimensional homology groups are 0 because there are no high dimensional simplices in your complex. So that's a calculation of the sphere. And to general, quite general conclusions from, well, from this rule that for a simplicial complex, you just use the simplices that you see there are as follows. When you have a finite simplicial complex, the homology will always be finitely generated, because there are finitely many simplices in your complex, and these are the only ones that you need to use to calculate homology. So the groups, the chain groups and cycle groups and boundary groups and homology will be finitely generated. And then it vanishes above the dimension of the complex. So that's not really visible from the singular definition. There are maps from high dimensional simplices into a space, but in a finite dimensional simplicial complex, the dimension of the complex is the top dimension where homology may appear. It will vanish in high dimensions. All right, and to finish, let me repeat Brover's argument. So I haven't said that, but again, homology is a functor. So when you have a map between spaces, then you can use it to push singular simplices from the source to the target. That induces a map on homology groups. And then you can perform basically the same argument that we did for the 2-dimensional disk, but high dimensional disks. So again, a map F gives you a map G, which from the disk to the boundary, it is equal to identity on the boundary, and therefore, when you apply the n-1st homology, and it vanishes for the disk, it is Z for the sphere, just as we did for S2. The second homology was Z. For Sn-1, the n-1st homology would be Z. To say, take a boundary of an n-dimensional simplex and take all the facets to construct a cycle. And everything between 0 and n-1 vanishes. So in n-1st homology, you get the same diagram as we had in the 2-dimensional case, and we get a contradiction. All right, that's homology and
a break, maybe?
Probably, yeah.
Okay. Any questions? Okay. Any questions from the people online?
Can I actually ask one question?
Yeah, sure.
Can you hear me?
Yes, I can hear you.
Yes, so fundamental groups are actually the free groups generated by the holes in some sense, yes?
Well, to some extent, yes, but for example, for a 2-dimensional torus, this is the free abelian group, is Z². So there are sometimes relations involved. These are not always free groups. There might be relations coming from the high dimensional pieces of the space.
Yes, but isn't it true like a free group generated by one element is abelian, and this is the case. So if I take like some manifold or with 2 holes, I will get a free group generated by 2 elements or something else?
No, you may you may get any group at all.
Any group? Oh, okay.
Any finitely generated, let's say. So if you have a presentation of a group, you may perform the following procedure. You take a circle, 1 circle per each generator. You glue them at one point. So it's a bouquet of circles. And then for every relation, you glue a two-dimensional disk so that the boundary of the disk is glued along these circles according to how the relation proceeds. And if you glue those disks, you obtain a space whose fundamental group is your favorite group.
Okay, thank you.
Okay, any other questions? Okay, if this is not the case, let's stop the first part and reconvene at 12:25.
Taka uwaga, plan został zaktualizowany i pełna jakby aktualna wersja już.
Okay, we start the second part. Okay, no, not more because you will not be visible. Okay.
Okay, so let's start the second part. I still have one more functor to talk about, which is cohomology. And you will see some, hopefully we'll get to some reasons why I'd like to discuss this also. So, so cohomology groups are also certain groups associated to topological spaces. And the terminology is just the co-terminology of homology. So there are co-chains, co-cycles, co-boundaries, and cohomology groups. It's very similar in terminologically, and in a setup, it's also quite similar. So what are co-chains? I will need co-chains with coefficients in some abelian group A. So I used coefficients Z, integers, for homology groups, but here I need slightly more sophisticated things. So let's say I have an abelian group A, which sometimes is a ring or a field, but let's say for now it's a group. And what are n cochains with coefficients in A? These are just maps from the set of singular n simplices in my space X to this group. So to every singular n simplex, I'd like to associate an element of A. It could be a real number, for example. So to every singular n simplex, I'd like to associate a real number. And those things, singular, which means it means a map from the standard simplex to my space X. So these things do appear in analysis, for example, when you have when you have a holomorphic function in some domain in the plane, and you integrate it over curves. And a curve is a singular one simplex, and this integration assigns a complex number to this singular simplex. So that's an example of a cochain. There's an issue of differentiability here, which is a bit subtle in various situations, but you could use smooth simplices or differentiable simplices over which you can integrate. In this situation of holomorphic functions, in fact, you can use all singular simplices. In other contexts, there are differential forms that can be integrated over simplices, and that again leads to constructing a cochain from a differential form. Right? You integrate a given differential form over a singular simplex that gives you a number, and in that way you get a cochain. So there are examples naturally coming from analytic situations. And then the set of singular n simplices is a basis of a chain group. And therefore, if you have a map on a basis, that extends to homomorphism from this free abelian group generated by the basis. In other words, you can regard n cochains as homomorphisms from this singular chain group to your group A. So S upper nx, the group of cochains, is just the set of homomorphisms from the chain group to A. And then there's this co-boundary map. So let me try to indicate how it's constructed. We have the chains of dimension n. We have the boundary map from Sn+1. Right? That's the previous section, the boundary map from n+1 chains to n chains. And then if I have a cochain, then this is just a homomorphism from this Snx to A. So that's phi, which is an n cochain. So when you have this diagram, it's obvious what you do. Compose the two arrows, compose the two maps, and you get phi composed with delta. That's an element, that's a homomorphism from Sn+1 to A. So it's an element of the cochain group of degree n+1. And that's what we define to be d phi. So in a sense, it's just like the boundary, but since you pass to the dual objects, it gets dualized. It goes in the opposite direction. And also corresponds nicely to those analytic situations. In the space of differential forms, you also have the exterior derivative d, which enlarges the degree. Okay. So once we define that, we can define the cohomology group, just as before, dividing the kernel of this d by the image of d. So you get some groups, and let me say that for nice spaces and nice coefficients, these groups do not come out very different from the homology group. So for example, if you use real coefficients and you have a finite simplicial complex, then both homology and cohomology will be vector spaces of the same dimension. So at first sight, you don't get much new here. But there are some slight differences, and let me go to them. So first, there's a relation between one thing and the other. So those cochains were maps from chains to your group, and therefore you can get a pairing, taking a homology class, a cohomology class, and well, evaluating one on the other. So a homology class, is the class of some chain, and the cohomology class is the class of some cochain. And if you have two such things, then you can map this pair to just phi of C, right? But the cochain is something that you can evaluate on a chain. So you can apply phi to C and get an element of A. But that gives you a map from a product to the coefficient group, and it's a quite important map. In many situations, it's a perfect pairing. It identifies one space with the dual of the other, but not always. So that's denoted also, maybe I use a different color. It is quite often denoted just like scalar product. It's a pairing between a cohomology class and a homology class. So there is something to check here. I defined this pairing using representatives, right? So you need to check that the result does not depend on the chosen representatives. It is really well defined on homology and cohomology. Okay, now there comes some difference with homology. The difference is that maps between spaces induce maps on cohomology groups, but going in the opposite direction. So let me try to explain. Suppose you have a map from X to Y, map between two spaces. Then this allows you to map chains in X to chains in Y. You just compose with F, and you get a homomorphism between those groups. Now, if I have a cohomology class, it's represented by some cochains, a map from S and Y to my favorite group. And again, I can compose the two maps. So if the cohomology class was on X, then the two maps I'd have on the diagram would have a common source and would be non-composable. But if I take a map from S and Y to A, I can consider the composition, and that composition is the F star phi. So maps between spaces, induced maps between cohomology groups, but going in the opposite direction. And again, if you saw some differential forms, you probably know that they pull back their maps. They don't push forward, they pull back, just exactly like cohomology classes. Then that's a major difference. Another major difference is that if your coefficient group is a ring, for example, a ring of integers or reals or rationals, then you can define multiplication. So let's say you have some space and two cohomology classes, one of the dimension k, one L-dimensional. Then you can form a cross product, alpha cross beta, which will be a k plus L-dimensional class in the product of spaces. There's some natural definition. For example, well, on the level of cochains, you'd like to define a cochain on the product. Suppose you have a k plus L simplex in the product. You can project it onto factors, project it onto X, project it onto the other X. And then you get singular simplices in the factors. And after those projections, you restrict. So in the first factor, you restrict to the, say, front k face, so the subset of the simplex spanned by the first k vertices, and evaluate alpha on that. In the second projection, is restrict to the back k face, the face spanned by the last k plus 1 vertices of your simplex, and evaluate beta on that, and you multiply the results. So that's a definition of cross product. And there's a similar construction for homology also. So you can do those cross product of classes. But then there's the vertical arrow, which allows you to pass to a class in X. From a class in X cross X, you pass to a class in X. And the trick is that there's a diagonal map. There's a map delta from a space X to X cross X. It just maps a point to the per X. And you define alpha cup beta, that's what it's called, just as the pullback via this map of the class alpha cross beta. So if you had homology instead, and this diagonal map would push classes in X to the product, and having this cross product in X cross X would be no good. Like you wouldn't be able to transport it to X because the map goes in the wrong direction. But here, as cohomology is contravariant, it pulls back via maps. You can pull back your class alpha cross beta from the product to the original space. And in that way, you get an algebra structure in cohomology. So that's a major difference. Let me finish the discussion of cohomology by giving you an example. I won't calculate things, but I will tell you what the answer is, and it will be an example where cohomology works better than homology. So I'd like to consider two spaces, CP2. So CP2 are just one-dimensional complex subspaces in C squared. Dimensional linear subspaces. C squared of C cubed, sorry. C cubed, and then S2 wedge S4, that's the bouquet of spheres. So you take S2, you take S4 and glue them at one point. I take two spheres and identify one point in S2 to one point in S4. So you get a pair of spaces, and let's try to to see what the homology groups are. So for CP2 and for S4, but with various degrees, so 0, 1, 2, 3, 4, 5, so on. So both spaces are connected. So in dimension 0, you get just Z. In dimension 1, you get 0. So for spheres, it's quite natural. For CP2, it requires some calculation. In dimension 2, you get Z in both cases. So for the spheres, the Z comes from the cycle in S2. And then there's a cycle coming from S4 and then zeros. And for CP2, it turns out to be just the same thing. It's a four-dimensional manifold, in fact. So the four-dimensional, you can triangulate with CP2, and two-dimensional simplices, four-dimensional simplices give you a cycle. And then if you want to see the two-cycle, you can restrict to subspace. You can consider one-dimensional subspaces of C² sitting in this C3. And these subspaces of C², they form a sphere. And that sphere gives you a two-dimensional. So these are homology groups. And as you can see, they are the same. So homology does not distinguish the spaces. Okay, from the topological point of view, you could say they are obviously non-homeomorphic because, well, the second one at some places is two-dimensional, at some others four-dimensional, and the first one is four-dimensional everywhere. But remember that those invariants are stable under deformation. So the spaces can be deformed by stretching and squeezing. And then you could imagine that starting from one of them by stretching and squeezing, you could arrive at the other. The squeezing can change dimension. So the technical term is homotopy type or homotopy equivalence, which has appeared 2 days ago already. So the correct question to ask here would be, are these spaces homotopy equivalent? And those factors of algebraic topology, they are stable under homotopy equivalence. So they are good to answer this question. Homology says, well, we don't know. It comes out the same for those spaces, so you don't know. But if you look at cohomology, you get the same groups, but you can calculate the multiplication. And the multiplication is as follows. Okay, for S2 and S4, there are, let's say, generators X here and Y here. And the potentially non-trivial multiplication is X². If you multiply X with itself, turns out you get 0. But that's somewhat expected because this generator comes from the two-dimensional sphere, and inside the two-dimensional sphere, there's no four-dimensional cohomology. So in a sense, those cycles do not interact, and X² has to be 0. While in the CP2, there is a generator of the Z, and its square is the generator of the Z in dimension 4. So that's not easy to calculate from the definition, but it's quite standard to calculate using the machinery of algebraic topology. And you get two different algebras, two different cohomology algebras. That tells you that the spaces are different. So in that way, cohomology is a stronger invariant. It has extra structure. In some situations, this extra structure allows you to distinguish things that homology cannot distinguish. Okay. So that's, yeah, sure.
I don't know. I don't see maybe something, but why is it so that the top cohomology is these squares? This space is orientable. Yes, am I right?
Yeah. Right.
So the top cohomology should be Z. Yes.
Yes, it is. And okay. So what I maybe sorry, maybe I'll use some different. Well, I'm not saying it's Z². It is Z. What I say is that the Z in dimension 2 has a generator. Let me call it different. Let me call it W. Okay, there's an element in this Z, which is W, which is the generator. And if you calculate W², it's not 0. it is the generator of the Z in dimension 4.
Okay, so in other words, all cohomology groups are the same, but there is no map between these two spaces which would induce an isomorphism on cohomology. Yes?
And preserve multiplication.
And preserve. It's
So,
automatic, yes? Or not?
No, the multiplication in this lower line, multiplication is trivial. Right? You multiply x by itself, you get 0.
But if I have a map in between spaces, then it induces a map between cohomology groups, and then this map is a homomorphism of rings. Yes.
Yeah.
Okay. Okay. Thank you.
So that's the end of the discussion of these basic functors. So if there are any more questions, that's a good moment. Yeah. Yeah, well, I think I don't want to yes, there are such examples.
Is it possible that homology can distinguish an opposite? Cohomology can't distinguish spaces, but homology can?
It seems to me that there is a universal coefficient formula, yes, and you can compute cohomology with homology, yes.
Yeah. Yeah, so I'm yeah, so yes, it is. There's a universal coefficient formula which allows you to calculate cohomology groups once you know homology groups, but it doesn't allow you to calculate the ring structure. It's still I'm not sure what's the answer. So it's still probably possible to have different homology groups, and the universal coefficient formula maybe gives the same cohomology. Yeah. So okay, I'm not sure at the moment. Okay, never. Yeah. All right. So okay. So let me try to pass to bundles. I'd like to introduce some more general machinery to describe the question I started with. What is a bundle? And I'd like to talk about flat bundles. So how to build something that's called a flat bundle. There are many ingredients for that. And the ingredients are as follows. So first, you need a fiber. So a fiber will be something like this green interval. The examples at the beginning, the fibers will sit over points of my base space. So over every point, I will have a fiber. And this fiber could be essentially anything. typical examples, it's either a vector space or topological space, a simplicial complex, but it could essentially be anything. It could be a monster model of a stable theory, if you wish. Then the next thing you need is a group acting on F. So remember, as we went along a loop, we came back to the original fiber, but it got glued to itself by some non-trivial transformation. So we need a group of possible gluing transformations, a gluing group. That's a group of transformations of F, a group acting on the fiber F. You need a base B, so a space over which you will build your bundle. And then to actually perform a specific construction, you would need an open cover of this B, covered by open sets, and some gluing functions, some locally constant functions defined on intersections of the sets of your cover. Locally constant because I want to build a flat bundle. And they should satisfy certain compatibility conditions, which I'm not stating here. And then the construction proceeds, the building procedure proceeds as follows. Start on the left from this cover of your space by open sets, and then you separate the sets. So you think of each set as a separate space, and you consider a product. So over each space, your fiber bundle will be a product. So you take UI cross F, UJ cross F. And that comes with a projection onto the first factor. So this gives you a so-called trivial bundle over your set UI, just the product with projection of the first factor. So over each point of UI, you see a fiber F, and all those fibers are identified. They are identical to F. And then you reglue your space. So you reglue the sets back to your space X, and as you do that, you also need to glue the fibers. So if you have a point P which is in two open sets, UI and UJ, then in the mid step you saw two fibers over that. There was a fiber F sitting over set UI and a fiber F sitting over set UJ, and they were both over P. Now you want to glue those two copies of P, so you need to glue those two fibers. And you do that using a group element. So that's why these functions Gij are necessary. You glue an element F from the I fiber over P to the element Gij of P acting on F from the J fiber over P. Okay, so you glue those green trivial bundles together, identifying fibers by transformations from the group G, and the local gluing functions Gij tell you how to do it. So once you do that, your products UI cross F get glued to a so-called total space E. So in the original examples, this was a cylinder and the Möbius band. So that's the so-called total space. And the projection onto the first factor survives. So after the regluing, you still have projection to B, map to B. And pre-images of points are still, in some sense, they are F. But they are F in many possible ways. So a point B could sit in several open sets, and once you focus on one of these sets, the fiber is identified with F. If you focus on the other set, again you have identification with F, but these identifications are slightly different. They differ by an element of the gluing group. You have identifications with F, but they are a bit fuzzy. There are several possibilities. And another feature is that if fibers are close, if your points B and B prime are close, then the fibers of them have a privileged identification. So if your 2 points are in the same set UI, then the fibers are identified with F using this I've trivialization, and then you can use the identity map to identify them. If you pass from UI to UJ, So if your 2 points are in the same connected components, say of the intersection ui and uj, and when you pass to uj, the identifications with f are different, but the difference is the same element of the gluing group. So the fibers, the identification of the fibers with themselves, one with the other, is the same. Doesn't depend whether you look, you take it from the set ui or from the set uj. If you want to identify them with f, that depends on which set you choose. But if you want just to say they are identical one to the other, it's correctly defined for points that are close. All right. But then this is no longer so if you travel in your space along a long loop. So let me try to explain that. Okay, so suppose I have this space X over which I build a flat bundle, and I have, let's say, a loop here. So this loop can be covered by those sets UI. Those UI cover the whole space. So in particular, they cover this loop. And then I want to travel around this loop. So I choose some points in the intersections of those sets, the points where trivializations switch. And over each point, I have a fiber. So I have a fiber here, I have a fiber here. And the 2 points are in the same set UI. Therefore, there's a well-defined map. There's a well-defined identification. Then, okay, there's a next fiber over this set. And these 2 fibers are in the same set, so there's a privileged identification. And then there's an identification of those 2 lower fibers and the map here also. So each consecutive pair is in the same set UI. So there's an identification of the fibers. But as you travel along the whole loop, the final identification may not be identity. So you may start with a point, map through all these maps, and come back to something different. And this difference is the monodrom. So here, let's say this is the loop. This is the loop gamma, and that's what we call rho of gamma, the monodrom. So rho is can be defined as a homomorphism from the fundamental group with gluing group G. Okay, so to define it correctly, you need to say first you consider loops that start from a given point, and then the fiber over that given point should be identified with F in some way, and then all these monodromies give you elements of G. That's how you build the monodromy representation. So this is a representation of your fundamental group into the group G, a homomorphism from the fundamental group to the gluing group G, which tells you how the bundle twists over various loops in the space. And the basic fact is that there's a bijection between isomorphism classes of flat G bundles, objects that I described to you how to build, and homomorphisms, those monodromies, so homomorphisms from the fundamental group to G, modular conjugation. And so where's that conjugation coming from? We look back to really, okay, so the monodromy assigns to elements of the fundamental group some automorphisms of the fiber over a point. And to actually get an element of G, you need to identify this fiber with F. There are many possible identifications. If you change identification, it results in conjugating the representation. It's like, if these were vector spaces, a monodromy would give you just an automorphism of the vector space sitting over some point. And if you wanted to get matrices, you'd need to pick some basis in this vector space. And well, if you change a basis, you get different matrices, but it's conjugated by the transformation map between the bases. But that's the effect here. So conjugating representation doesn't really change the geometric information. It's a different way of describing it by matrices. That's how you can think of that.
Excuse me, I have a quick question because this resembles the holonomy group. And I always struggle, what's the difference between monodromy and holonomy? Could you maybe have an answer or a quick comment on that?
Here, there's no difference. Like holonomy is defined for bundles with a connection. And here, when the connection is flat, when the connection has trivial curvature, then you use the word monodromy also.
But can you define monodromy for non-flat bundles?
I would say no. I mean, you can define holonomy, but then you don't call it monodromy.
Okay, thank you.
It's a terminological.
Does the word conjugation there depend on did we choose topological space or vector space for the fiber?
No, it's conjugation in G.
Ah, right.
First, there's group G, and where conjugation means composing this homomorphism with an inner automorphism of G. Okay, so bundles, they are somewhat similar to cohomology classes. They also pull back. There is a question in chat. Okay, thank you. Is X equal to B? Yes, it is. Thank you. So let me put B here. Was it also enough? Yeah. Sorry. Okay. Bundles pull back. Let's say I have a bundle E over some space Y and a map F from X to Y. And I can form something, the pulled back bundle F star E. And the way to think of it could be as follows. I write it formally below, but maybe I say first, what's the fiber of that bundle over X? Well, you just map X to Y. So you take the point F of Y, and over that F of Y, the bundle E has its fiber, and I just declare F of X. Yeah, thank you. And I just declare the fiber of the pulled back bundle over some point to be the fiber of E over the image of this point. More formally, it's described as follows. F star E, the space, is the set of pairs X, E, such that F of X is the same as the projection of projection map. All right, so in that way you get F star E, the pulled back bundle. So for example, if your map squeezes X to a single point in Y, then the fiber over that single point will get replicated over the whole of X, and your bundle will be trivial, just a product of X with that fiber. But if your map maps some non-trivial loop in X to a loop in Y over which the bundle really twists, then the twist will be pulled back and replicated in X. Okay, and then the algebraic apparatus to describe twisting of bundles is the apparatus of characteristic classes. So what are characteristic classes? It's the following thing: to every G bundle E over any sufficiently good base B, I'd like to assign a cohomology class in certain K group, HK of B, so that the classes assigned in that way pull back in the same way as the bundles pull back. So that's a formula, and let me draw the diagram as well. So I have a map, let's say F from X to Y. I have some bundle here. And I have the pulled back bundle. And these have their cohomology class. Let's say this characteristic class assigns a certain cohomology class to E. That should sit in some HK of Y. And there's also the same characteristic class assigns a cohomology class to F star E. This should sit in HKX. And there's a map on cohomology, which goes in the direction opposite to F. So you can compare these two classes. You can map C of E to HK of X, and you want it to coincide with the class of F star E. Sure. No, G is, there's no G in this picture, but G is this gluing group, okay, which, so I'm considering bundles with, let's say, built from a fixed fiber and with a fixed gluing group.
Yes, but I'm somehow confused. I try to imagine what happens for a vector bundles. And in the case of vector bundles, okay, one can associate it with every vector bundle, principal bundle, for the so-called frame bundle. And then this structure group is different, for example, for complex and different for real bundles. And also the theory of characteristic classes takes care of it, namely for real bundles, one gets classes with coefficient in Z2, but for a complex one, we get classes with coefficients in Z. And here somehow I don't see any reference to coefficients. So I'm a bit confused.
Yeah, that's right. So I wrote just HKB, and this is some. There might be some coefficients A, which are not written here. And,
but is this A somehow built up from G canonically?
in this general definition, no. Well, it may be that no class like that exists. Okay, if you choose wrong A and wrong K, it might be that there's no class like that, or there's only the zero class, which is not interesting.
Okay, so at this moment we are not interested in coefficients, yes?
Yeah. But,
maybe it will come later.
It will come.
Okay, thank you.
Or not. All right. So a characteristic class is like a way of making a shade of bundles in cohomology. So there are spaces, there are bundles over that, and there is cohomology of those spaces, and you'd like to assign cohomology classes to bundles in a way compatible with pullback. All right. So yeah.
Does not exist in some situation.
It may happen that yeah. Or it may happen that there are many. So there might be many characteristic classes. One of the objectives of the theory is to construct various characteristic classes of bundles. So they may exist, they may not exist. And I'd like to show you some way of constructing a characteristic class for SL2K bundles, say with fiber K squared. The fiber will change. The gluing group is what is really important. You may change the fiber, and Those gluing instructions are really what tells you what the bundle is, how it twists. But let's say I'll focus on the case where G is SL2K, it acts on K squared. So SL2K are 2 by 2 matrices with determinant 1. Coefficients are taken from some field K. I take infinite field, but no other assumptions. And the fiber is K squared. And the base I'd like to consider is just some surface. I'd like to construct a second cohomology class. And okay, the way to proceed is to first, you can modify the fiber. So suppose we have a bundle with fiber K squared over the surface, this K squared twists in some way. And there are some gluing functions that describe that. So you can replace the fiber with essentially any other fiber on which you have the action of the gluing group. For example, instead of K squared, you could use P1 of K, the projective line over K. So one-dimensional subspaces of K. So SL2K acts on K squared. It also acts on lines in K squared. And therefore, you can glue the same sort of bundle from the same gluing, with the same gluing functions with fiber P1 of K. And then the next step is a bit weird. I'd like to consider the infinite simplex with vertex set P1 of K. So this P1 of K, this projective line, is an infinite set. It's the field with infinity added in a sense. So I'd like to span a simplex on each finite subset of this set. It will be an infinite dimensional simplicial complex, but individual simplices in this complex will be just finite simplices. So every finite collection of lines spans a simplex. It's a set of vertices of a simplex. So from a bundle E with fiber K squared, I can produce a bundle E of delta, which is glued in the same way using the same gluing function SL2K, but whose fiber is this E of delta, this infinite simplex. Once I do that, I can choose some section. So, so I'd like to choose a section in the following way. For every simplex in B, I pick an element of the fiber. So over each vertex of a simplex, there's a fiber. This fiber is a copy of this infinite simplex with vertices being elements of P1K. So I choose one of these vertices. I choose a line in K squared in a sense. And if my simplex is small enough, if it is contained in one of the sets UI, then all those fibers may be identified, and I can regard those points S of 0, S of 1, S of 2 as just 3 vertices of my infinite simplex. And as it is an infinite simplex, they span a triangle there. And this triangle is not well defined because if you change the trivialization, if your simplex is in UI and UJ, then those sets allow you to identify fibers in different ways with this delta. But the difference is an element of the gluing group, an element of G. So this triangle is well defined up to the action of G. So now suppose I had a cocycle on this infinite simplex. To cocycle, it would be G invariant. Then I could evaluate it on this triangle and get a well-defined answer. The triangle is not well-defined, but it's well-defined up to G. So if my cocycle is G invariant, then the effect of the evaluation is a well-defined element of the coefficient group. So I proceed in that way. I choose a section, and if I have a phi, I evaluate it, and in that way, I assign values to triangles in my space. So I get a cohomology class of the surface with the same coefficient group as this phi. So there's a mysterious ingredient phi, this G invariant 2 cocycle, that if I have it, then this procedure gives you a certain cohomology class of the base, which tells you something about how the bundle twists. So let me try to say at least a few words about how this G invariant 2 cocycle is constructed, because that's the very interesting part. So it is constructed in a tautological way. So first, you need to, okay, you want a homomorphism from the chain group to some group, and the first step is to say, okay, I'll just take identity. I will map a chain to itself. And the drawback of that is that it's not a cocycle. So for example, if your chain is a boundary, then a cocycle would map it to 0, but this procedure maps it to itself. So the cure is divide chains by boundaries, right? Divide by the group of all boundaries and assign to a chain its class in this quotient. And tautologically, it becomes a cocycle, but it's not yet G invariant. So the next step, okay, I'm looking here, okay, I'm looking here now. The next step is to force G invariance. So divide this chain group also by differences, C minus GC over all chains and group elements. It might become pretty small, right? It might become trivial. That's a fear. But if you do that and get something non-trivial, then your tautological cochain becomes both a cocycle and G invariant. So there's the cochain, there's the G invariant cocycle, and there's the coefficient group, and the question is, what's this group? And it turns out that this group is non-trivial. And as I'm running out of time, let me skip a bit lower and tell you what it is. It can be calculated from linear algebra. It is spanned by lines in k squared, okay, with some imposed relations. If you calculate the relations, you get the following description. You should take the free abelian group generated by the quotient k over k squared. So this k dot is just k with 0 removed. So you take the multiplicative group of k divided by the group of squares. So this may be a small group, like for reals, it is a 2-element group, but for rational numbers, it is quite large. You span a free abelian group on that, and you divide by the relations that are written here over all possible A's and B's. And you still maybe don't see from this description whether it's trivial or not, but it turns out that this coincides with well-known algebraic objects. It is the Witt ring of quadratic forms. It is considered by Ernst Witt in the last century, not yet 100 years ago, but almost. And so it's been calculated for various fields, and there's a vast algebraic literature on that. It's in many cases, it is quite non-trivial. So in that way, you do get a non-trivial group and a non-trivial cocycle and a non-trivial characteristic class. And so questions are, yeah, maybe I'll try to state some questions. So questions are, what values this class may take? For example, is it really non-trivial? The group is non-trivial, the cocycle is non-trivial, but maybe if you evaluate it on flat bundles, you get 0 all the time. That's a fear. So there are some restrictions that can be established, and so some classical ones, some less classical ones. And we did actually some computer experiments for the rationals where this group is quite non-trivial. So we know that the value of this characteristic class sits in some subset of the Witt ring, and the subset for the rationals is like here. It is Z plus an infinite direct sum of two-element cyclic groups, Z mod 2s. Like for every prime versus Z mod 2. It is some part of the Witt ring, and the class takes values there. And the integer part is pretty well understood. It's coincide with a classical Euler class, but those prime components, they are much more mysterious, and computer experiments tell you that these are non-trivial. You can write down representations, run Waldeck-Hebsch's program on that, and you get non-trivial, or run FreeCAS. Okay, you have to write your program in FreeCAS, but the system lets you do that, and you get examples with non-trivial classes. But an open question is what collections of primes do really appear. Non-trivial collections do appear. You can get examples, but we have no theorems about the general behavior of those collections of primes that you do get over a given surface. Okay, so I guess I should stop. Thank you.
Okay, any questions? Oh, there was you check
Yeah,
chat. Okay, any questions?
Yes, I have a question. On the previous slide, we had the quotient group or the group, but how do we divide by k squared or k dot squared if it's not like a subgroup of k?
It is so this k dot is the multiplicative group of k, so k with 0 removed, and k dot squared is the subgroup of squares. It is a subgroup of the multiplicative group. The squares of non-zero elements in the field.
It's not Cartesian square.
No, it's not Cartesian.
Okay,
sorry, yeah, I should maybe. So this k dot squared is just the set of elements of the form a squared over o n. K dot, yeah. This is the set of squares in the field.
Okay. Have a look at chat.
So the computations of the Witt ring that I know of are purely algebraic. Right?
Okay. Any other questions?
Yes, so just going back to this dividing by k dot square. Okay, this is you mentioned that this is a subgroup, but is it normal or not?
Yeah, the field is commutative.
Oh, okay,
so
everything is commutative. Yes. Okay, sure.
Well, again on chat. Thank you very much. Okay. Well, any question from people online? Okay, if not, thank you. And